Some of the page numbers don't, and example numbers don't match up, but we are on, in your book, page 46, example 5. So this example takes this whole page. We're going to answer a whole bunch of questions about this one scenario, this one word problem about hitting this golf ball. So again, you can kind of think of a golf ball being shot off of a tee or off the ground and making a parabola kind of shape before it comes back down and hits the ground again. So again, there is a formula for this scenario, and you're going to see this formula a lot in physics, because this is really a physics problem. It's a math problem, but it's also a physics problem too. So Claire, she's hitting this shot off the tee, and this is a formula to calculate the height. And the height is a function of time. So the height is h, which is going to be our y value, and it depends, it is the dependent variable on how long that ball is actually in the air, which is the t. So the first thing it asks us to do is factor the function to find our zeros. So if we take our function, put it in standard form, which means set it equal to 0, and I'm going to solve by factoring. So I'm going to take out a minus 16t, and I'll end up with t minus 5 equals 0. Set each one of the factors, I'll do this over here, equal to 0. Minus 16t is equal to 0, or t is, of course, equal to 0. And the second factor would be t minus 5 is equal to 0. T is equal to 5. So this is 0 seconds and 5 seconds. And the second part of this says, what do these numbers represent on our graph? What does this mean? What does this mean? Well, remember that these values that we have solved for are when you are intercepting the x-axis. So your height is 0. That means that at 0 seconds, before she's ever hit it, and at 5 seconds, her ball is on the ground. It leaves at 0 seconds, and it is back down at 5 seconds. And these are the 2 points on the x-axis where y is 0 and x is, at the x-coordinate is 0 and the x-coordinate is 5. We could actually write these ordered pairs looking like this. And we're going to use that in a minute to graph. Okay, so now we're going to go down on part B, and it's asking us to create a table of values in order to be able to sketch the graph. So at 0 seconds, we have gone nowhere. We are on the ground. And then we can just kind of use increments that make sense. We had 5 seconds being when it's back down on the ground. So in between, of course, we can do 1, 2, 3, or we could do something in between. I'll actually just make another entry in here and do 4 as well. So at 1 second, and this is, plug it in. So at 1 second, you plug it in and you figure out, you can do this on your calculator or you can do it by hand. But when time is 1 second, you plug it in and you end up with 64. And this is feet. Let's see. What unit are we in? Feet, height in feet. Okay? At 2 seconds, it's higher. At 3 seconds, it's the same as 2 seconds. That's strange. At 4 seconds, oh, it's the same as it is at 1 second. So what is that telling you? It's telling you that right in here, somewhere, probably at 2.5 seconds, it's at its peak. So it's coming up from the ground, peaking, and then, this is a terrible graph, but you get the drift. It's going back down. So it's at 96 in 2 places, 2 time segments. It's at 64, and of course it comes back down to the ground. So in answering part number C, it says, how long is the ball in the air? After it leaves, How long is it up in the air? Well, that's this guy right here. It's up in the air for 5 seconds. And then the next question says, what's the maximum height? So we look at what we've got in our table. We've decided that between 2 and 3, it's at its peak. Well, in between 2 and 3 is 2.5 seconds. And we need to plug that in to our calculator and figure out what the maximum height of the ball is. And I have not done that, but you can do that. T is 2.5 seconds. And then the max height would be the answer to, when you plug it in, the minus 16, 2.5 squared plus 80 times 2.5. What is the answer to that? Okay, then it says, how long after it's hit does it reach the maximum height? Well, we just talked about that, 2.5 seconds. Oh, I did do this, the maximum height. I did. I plugged it in, and I got 100. So see if you get the maximum height of 100. I was thinking I hadn't done it, but I did. See if you get that. And then it's asking just basically for a plug and chug. Okay, well, we know what the height of the ball is for our table entries, and we figured out that it's at 100 at 2.5 seconds. But now it's saying, all right, well, tell me more specifically, what's the height of the ball at 3.5 seconds? So again, you plug it in, the formula, and you let T equal 3.5. And when you do your calculation, hopefully you've got this figured out on the calculator, I get H is equal to 84 feet. And then it says, is there another time at which the ball is the same height? And it's talking about F. So we know it is because it's on the other side of when it's going up and it's coming down. So we've determined that at 3.5 seconds, it's coming back down to 84. Well, we know it had an 84 going up. So it would be at 1.5 seconds. How long is the ball? 64 feet or higher in the air. So you go back and you look over here. How long is it more than 64? Well, it's all the way from 1 to 4. So between 1 and 4 seconds, it's left 64 going higher, 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 and it doesn't come back to 64 until the 4th second. So that's 3 full seconds that the ball is 64 feet or higher in the air. And then finally, the domain and the range, and then I'm going to try to graph it. I don't do so well with this tablet. So the domain, actually, let's graph it first, and then the domain will be easier. We have not labeled our axes. This is time. It's the independent variable. The dependent variable is the height. This time is in seconds, and this height is in feet. And your units are really, really important. I can't look at this graph and have it mean anything to me if I don't know what you're measuring your time in. Is it hours? Is it days? Is it months, years? And then the same thing for the feet. So the units, as you can see, would be really important. So we know what our zeros are. Starts on the ground there and comes back down at... oh golly, I have a different graph than you do in your book. Yours is better because yours is in steps of 0.5. Mine is not. Comes back down at 5 seconds. So I know that the maximum, the peak is at 2.5. This is where my axis of symmetry is going to be. And let me go back up and see what was that value. At 2.5, 100. So at 2.5, I can already tell you this isn't going to be pretty for me. Right there. So, okay, that gives us a nice basic shape of our parabola. And then we can go and we can look at 1 second. Where was it? 64? Okay, so 64, that right there. And then it was also at 64 at 4 seconds. So I can go do that. This is our axis of symmetry. And with any luck, I can sketch a little bit of the parabola. No, this looks absolutely like a kindergartner drew this, or worse. Can't do it. Okay, but you get the drift. You can do it. You have a better graph because the steps on your graph are more spread out than mine, and you can see that makes it easier to see what this graph is doing. So are there any other questions for us? The domain and the range. So basically, when you think about these parabolas, they're like flared U-shapes. That's what I call them, flared U-shapes. And they go forever, and they don't ever curve back in again. They're just continuing to go out, either steeply or very, very, very gradually. But they go forever, which means their domain is going to be every single point on the x-axis, which gives us a, oh, that's not right. That's not right, because this word problem, that's normal for flared U-shapes, but this is a word problem. So we don't have any negative x values for this particular golf ball. He is not in the air negative time. So our domain is going to actually be from 0 to 5 seconds. So in a word problem, it's different than just when you're doing a mathematical parabola that goes on forever. Our domain starts at 0 seconds and it ends at 0 seconds. So anywhere from, at 5 seconds. So a valid domain are the x values, which are these. And then the y values, the range values, is the height. So I'm going to go ahead and just put in my shell here. The height, of course, starts at 0 as well when it's gone nowhere. And our maximum point, we said, was 100. So that's our domain. This is our range. And we are done with this problem. So bring your calculators next class. We are going to work on page 47 in class. I don't really have a lot of confidence that I can do this calculator stuff and manage the tablet and manage the smartboard document at the same time. So just come back to class with your calculator, and we'll continue on page 47 in class. Thanks for watching.